Hi, everyone. My name is James Chapman, assistant professor in Department of Mechanical Engineering. Today, I'm going to talk to you about a dream I've had for a while now, and it's, can you design new materials simply atom by atom in a matter of seconds rather than the time it takes to do it today? And I'm going to talk about the example of catalysts. Now, we all like to eat food. It's probably a pretty important part of our lives. But a lot of times we don't think about where food comes from, the fact that we need things like fertilizer in order to grow them. Well, ammonia is one such chemical that is very important in things like fertilizer. When you think about ammonia, you have something like hydrogen and nitrogen. They have to come together somehow. That requires energy or effort in order to get them to go together and form ammonia. All a catalyst really is it's lowering that effort or energy in order for those two species to come together and form something like ammonia. So if we can reduce the energy that is actually required to make something like ammonia, then we can help reduce the climate impact of producing food, something that becomes more and more important as more and more people end up being alive. So when you think about designing a catalyst, there's a number of ways you can go into it. And for this talk, I simply don't have enough time, but you can think of these two scenarios, and they're very contrived scenarios, but pretend that they're the two big ones. The first is a single element catalyst. Take something like platinum, and imagine you have a surface of platinum. There's many different ways you can design that surface to help reduce the energy cost to form ammonia, but you're really limited because you only have one element. You only have a certain number of arrangements that you can make. But when you go to something like a many element catalyst, or what's known as a high entropy catalyst, you can see there's a lot more colors there. They all represent different chemical species, maybe aluminum, iron, copper, whatever. The reality is that because I have more chemical species present in my system, I have an innumerable number of different possible chemical and structural arrangements that allow me to help tailor that energy cost a little bit better. So if we move towards something like a high entropy catalyst, this gives us the ability to potentially greatly reduce the amount of energy required to produce things like ammonia, but it's not limited to ammonia. So why haven't we done it yet, right? We understand the concepts. The problem is, you can see from these colors in here, the more species I add into this box, the more innumerable this gets, right? If I have 10 plus elemental species present inside my box, there's a virtually unlimited number of possible structural arrangements I can take. How do I know which one actually lowers the energy? There's no real way to know experimentally. You'd have to trial and error billions and billions of configurations, or potentially guess and get the right answer. Even simulations can't really help you here, because the simulations are going to take days at a time in order to evaluate even one of these. It's faster than an experiment, but there's no possible way to evaluate every single one of these combinations with even simulations. So this becomes a material screening problem. And anytime you hear this word, you're going to hear something that is associated with it, which is machine learning. Machine learning is a buzzword. Everyone likes it. The reality is it's glorified curve fitting, right? I'm taking some function that I have no idea what it is, and in principle, mapping it onto a set of variables. Where this becomes useful, though, is if I can take my atoms, I know what they are, right? It's a simulation. I can just place them wherever I want. If I can represent them somehow that a computer can understand, in this case, you can see a nice picture of a graph. It took me a very long time to make that. Ultimately, I can feed that into my machine learning algorithm, teach it the physical laws that drive my simulations. The benefit of doing this is that now I don't have to take days at a time for every single one of those calculations. I can do this in a matter of seconds. And if I teach it well enough, it can identify not just the complex differences, but also help me go through and search that innumerable space. So rather than having to actually go in and calculate all billion possible combinations, I might only have to do a handful of them before I get the correct answer. And ultimately design a better catalyst or any material that can help the future.